Module 9. Now we're going to start to design the data path and ALU instructions. We're back to designing instructions. Now that we know how to build the transistors, we're going to start to put them together for the different tasks. So let's look at building multi-bit adders. We're going to use those to have an ADD or ADDI instruction. You probably know the 1-bit adder, full adder. We're going to make it multi-bit. And time versus space trade-offs, that's what they usually pay you for. Once we have an adder built, we're going to use the adder to build a subtractor. It's pretty cool. And then we're going to go to multifunction ALU, which is how CPU executes instructions using a MUX. What's the catchphrase for MUX? Many to one. Also, we're going to show you how to use decoders. So we start with MUX, we're going to show you decoder also. And then we're going to use adders to make multipliers. There's a shift and add, pretty cool. And we're going to be 2 different designs. This is the one that's usually used inside chips. This is the easy one to understand when you're getting started. And we show you dividers. I don't hold too much on it, but it's actually a multiplier running backwards. It's like a Carnot engine, and this is a Carnot refrigerator. Thermodynamics. Anybody? Do people take thermodynamics? Anybody? Raise your hand. Okay. If you give them their choice, okay, I guess they change this. You can choose or some dynamics or. You have to take, everybody has to take statics? Yeah. But I would say for ECEs, thermodynamics is probably the most beneficial because it relates to cooling of chips. And there's a lot, especially transistor level, if you're an electrical engineer and you're a materials guy, there's a lot of analogies there. So I like thermodynamics. Where are we in the chip? We're inside the ALU. Right now we're doing integer. This is going to be the next module. So right now we're designing add, multiply, and so forth. They're all integer. The next module we make them fractions and decimals. Our view of what we want to build, and this is the whole module to get there. So we start now with the goal diagram, and the last slide of this module is showing all the pieces. So this is the opaque box view, and we're going to build inside this box. So we're going to design hardware for all these instructions, plus some handling bits, some flag bits. So what we're seeing here is on the gold is a data path. So what does that mean? The bits flow in here as inputs, and the bits go out as outputs. The shape of this, remember I said our schematics, they always kind of give us a hint what they're doing. This is taking 2 inputs and combining them into 1 output. If it's dyadic, 2 inputs, 1 output. In the vertical dimension is control. In this case, we have some select control, which is our func field. Remember the func from module 6? Is one of our 6-bit fields in our instruction. Those bits are directly fed into this device. Turns out multiplexer is a good choice, or decoder. And we're going to turn on the function we want to execute, if it's add or subtract, multiply. And then we get some control information out. Was the result 0? Did we overflow? Question, how do we design ALU functions using Boolean gates? It sounds very complex. How do you build a multiplier out of and or? There's one great thing. We're using binary. It makes it so easy. This is the tip. I mentioned this, and now we're here. Every arithmetic operation is the same process as decimal. This is the saying that I have. It's my own saying, but is the right way to think about it. There's no such thing as binary arithmetic. There's only conventional arithmetic with binary numbers. It's the same arithmetic you already know. We're just not going to use any digits greater than 1. So why would you want to do that? Well, first of all, we're storing things as bits. We're computing as bits because transistors can do that very efficiently. But represented as bits, it's actually advantageous, and the circuit comes out much, much simpler. So for example, if you want to build an adder that's only using binary digits, it's just 0 and 0 is one case. The output is 0. 0 and 1 is 1. 1 plus 1 is 2, the same as decimal. We have to write it as 1, 0 because we have binary digits. Is there any other way to add 2 binary digits? No. What about the decimal case? There's 50 different cases. See, that's where your grades, 3rd grade, 4th grade, 5th grade, if you were just doing binary, you could have been a playground. Look, you had to remember this, they ask you this, then they ask you this, then they ask you this, then they quiz you, right? They keep saying until you think it's just makes sense, but actually they just brainwashed you. All these different cases. 7 plus 9. 16, right? Why is that? Well, actually there's no reason. It's just, here we only have 3 things to compute. Here, if you compute in decimal, you have 50 different cases you have to build a circuit for. We're going to turn this problem of computation into simple Boolean expressions. It turns out sum is very related to exclusive OR. It turns out to be a very important function for summation. The sum bit is actually just XOR. Multiplication is very related to AND. Let's start with adders. Here we have one of our 3 adder designs that you should know. This is called ripple carry adder. Ripple carry adder. We're watching the carry bits, ripple carry. The carry ripple from one stage to the next. You're going to say, all right. Well, the cool thing about this is that each stage is designed exactly the same. If I look inside this box, there's multiple ways to design it, but this is one full bit adder design. What's a full bit adder? Full bit adder has 2 bits and a carry coming in. What's a half adder? No carry in, exactly. We just have A and B, no carry in. That's called half adder. So full adder, we have A and B and carry in. This is how many outputs? A sum and a carry. Why? Because if you add 1 and 1, you get 2. How to represent 2 in binary? 1, 0. We need 2 bits of output. Here's the truth table. This is one realization of this truth table. You could take this truth table, throw it in a Carnot map, throw it in a design tool, and it will generate some gates, and you say, I want to use these gates. This is one way to build it. There's more than one design. Okay, this is just one design I'm showing you. So what's the advantage of this? Turns out that the gate count for this is relatively low in the sense that we design this one box, we just replicate it and ripple the carry from one carry coming in, goes into this box, and the A and B comes in. Where's A and B in our MIPS instruction? We're adding A and B, so where's A and B?
The registers.
It's RS, right, and RT. It's the registers. So on here, we're backing up, sorry, but now it's the time to see these. These are the input operands. We take a RS and an RT. Why is there, when RS and RT is 5 bits, why did I put 32 here? You got it. Speak up. That's the size of the operands. They're 32 bits. Each register is 32 bits. So this is the data that's flowing in. I select RS and I select RT, but they're each 32 bits wide. And they have a 32-bit output. It goes into RD. And now we see that we're going to design this one instruction at a time. Let's start with add. So we're saying that this has a space versus time trade-off. The problem with this, so the space is pretty good, but the disadvantage is propagation delay. What do I mean by propagation delay? I have to generate the carry out of the lowest, least significant bit as an input to the next most significant, and I have to generate that carry before I can start this computation. I talked to some people in office hours, talked to some people on pizza night. They were working late and studying. I talked about being able to do things in parallel, and sometimes we have to wait for one input to compute the next. Okay, maybe I just show you the same thing I wrote for them, because that's what's happening with these carries. All right, this is drawn as a circuit, but it's the same as software or an algorithm. Suppose you want to calculate A is x plus y, and B is A times 2. Okay. We add a semicolon, it makes it code, all right? It makes it fancy. Without a semicolon, people don't think it's code. So we put it there. We have statement 1 and statement 2. Question, can I execute statement 1 in parallel with statement 2? Yes or no?
No.
No, and you're right. Because I have to compute A before I can start this computation in statement 2. The same thing's happening here. I have to compute this carry out of this first stage of these. So in other words, I have to add A0 and B0. They're coming in here. They propagate through this gate, and then that goes to this gate, and then it goes to this gate. So the sum is ready after how many gate delays? 2 gate delays. If I told you this is 50 picoseconds, how many nanoseconds to generate the sum? 0.1. Yep. 0.100 nano. So that has to happen first before what? Before I can start adding the next bits. How many bits do I have to add in MIPS? 32. What's the problem with this design? It's kind of slow. Ripple carry adders are slow. So that's what we call disadvantage is propagation delay. I'm going to give you in the study set, we're going to do an example. How to calculate the propagation delay, because when you get a data sheet or you work for AMD, they're going to tell you this is a propagation delay of an individual gate. We need a CPI of such and such, which means this has to finish this whole thing in so many clock cycles, which means I know how I only have so many nanoseconds or picoseconds to do the whole instruction. Now you're getting somewhere. So what's on the next slide? Meet their performance requirement. One way to get the result quicker without waiting for these carries to propagate or to ripple is to use carry look ahead. Carry look ahead has these logic equations. You're not responsible to memorize these, but you should understand the concept is that what we're going to do is express all the cases when the carry could be 1. So start here. We say, when can this carry be 1? Well, carry can be 1 if A was 1 and B was 1, because 1 plus 1 is 2. which is the output is sum is 0, right? And what's the carry? 1. So that was one case that this is a 1. Is there any other case? Yes, speak up.
A is 1 and C always 1.
Exactly. So you can have either one of these 0 and an input carry of 1. You're going to have a carry propagate out. So this is called propagate and generate. We had the case when they're both 1. I did the generate, he did the propagate case. He's saying that the carry came in and is going to propagate out. So we get the full carry as the OR of either two cases. So we can write these equations. The only issue comes up as we go to predict ahead of time. If I have a carry at level 2, well, then I had it either generated locally or I propagated from the previous, which is dependent on propagating into that. And you end up with all these cases to OR together. And it turns out this is the Achilles heel. If you're a runner, Achilles heel is can break, right? It's a weak point. So here we need a very wide gate. This is the time to teach you guys this. In practice, we don't really build logic with more than 4 inputs. It doesn't work good as far as electrical characteristics. This gate's getting too wide. There's a saying, which is true, which is the difference between a block sliding down the frictionless plane in the real world, is that any Boolean expression can be computed in 2 gate delays as a sum of products or product of sum form. We use GD. 2 gate delays as a sum of products or product of sums. What does that mean?
It's a bunch of AND gates in an order.
Exactly. So we can take any Boolean expression and eventually get down to, here's a sum of products, right? I put AND gates here at this first level, and I have all the inputs here, and maybe I need more than, these are supposed to be AND gates. And then I need wider ones, but then I'm going to OR them together and I get Z. And I can do this in 2 levels. But what's the problem is if you want to do it in 2 levels, some of these gates may have a lot of inputs. We don't usually have more than 4, less than or equal to 4 inputs per gate. More than that, the capacitance is too large. The drive of the thing that feeds into that, there's too many losses, and it's just not practical. It's better to break it up. In practice, what they usually do is they'll do carry look ahead 4 bits at a time. And then they ripple those. So we've already said this. We're going to use a 2-level sum of products. See the 2-level sum of products? This is a product, this is a product, this is a product. We sum them together. So what does this mean? It means I can figure out C4 without waiting for C3, without waiting for C2, without waiting for C1. If each gate, if each gate is 50, go back to that, 50 picoseconds again, is the gate delay. How long does it take to generate C4 in a carry look-ahead adder?
50 picoseconds.
Say it, go ahead.
50 picoseconds.
You're halfway there. 50 picoseconds, so this is an AND gate, so that's 50. Then you've got this, then you have to OR them together. So it's 100 picoseconds, which we said is 0.1 nanoseconds. Compare that to ripple carry. A lot, because first you had to generate this, where C4, so first you did 50, the sum was 100 pico. The carry was even more, because we had 1 gate delay. I'm not wasting your time, this is the next question, we're actually calculating gate delay. So this is 50 to get to here, this output, because this box takes 50 picoseconds, that's what gate delay means. And then what? You have to put it into this box, is another 50, and then 150. And then what? You have to do another case of that, another case of that, another case of that. This is way faster, 100 picoseconds way faster than the carry look ahead, because it uses 2-level sum of products. What's the disadvantage?
A lot more gates.
Too many gates. If you have the area on the chip, you can put the gates there, okay, but maybe it gets too hot. That's a trade-off. Kind of getting wide here, right? Too many inputs. That's where I said you can ripple between the blocks as a compromise. That's usually the most usual practical design. So here are the carries we just computed, 2 gate delays. We're going to give you a problem in a minute. Our last design is carry select adder. In my opinion, this is the coolest one. This is provably the fastest adder you can design. How does it work? It's fastest addition approach. This is generating 4-bit adder using this design. So this is inside the clear box view. inside of here. Once we get that C4, we're going to use that to select two different cases. This is kind of cool. What we're going to do is we're going to add the next higher 4 bits. See, this is A3 and A0, B3 and B0. What are A and B? RS and RT, right? Is what? T0 and T1. I want you to be connected up, right? Connected up with what we're doing, right? ADD. T1, T2, T3. How many bits are inside T3? 32 bits, because this is a register, right? MIPS. Take the lower 4 bits is A, right? This is A, where's B?
T3.
Yeah. A is T3, so what's B? Okay, well, okay, this is A, so here's B. Okay. You can do A, B, B, A, right? It's commutative. Right? Then what? So this is the lower 4 bits, see, of the one register, and the lower 4 bits of another register. We add them together, we either get a carrier or we don't. At the same time, something else was happening. What was happening? We also took the next 4 bits of those two registers and did what? We added them under two different cases. What are two different cases?
0, 1.
Yeah, if it's like predictive. See this? We're leading you down there. Speculative. This is speculative execution. Say, I'm going to say, you know, suppose it's a 0. Well, I've already got that answer. Or suppose it was a 1. I already got that. Then what's the output that's going to go into T1? I said this is box does what?
Choose.
It chooses. It's a decision box. It's if. How do you choose one or the other?
It depends on C4. If C4 comes as 0, then you would choose
Exactly.
one on the right.
So what we're doing here is we're going to use the output to select in a multiplexer to choose one. So you're going to say, okay, well, I'm kind of getting this, but can you give me an example? So as you go with the Walmart with your friend, and you stand in two different lines. You're there with your friend or your girlfriend, and you go what, right? You stand here, right? And then what happens? Which line do you choose? The one that's done first. It's the same thing here. We're going to compute both, and when it's time to make the decision, you're just going to select whichever of the two was the right answer. When you stand in front of the line, you don't know. Like, you try to be smart about, oh, that cart gets all, but those are quick items, and then, well, that guy looks fast. He's a fast check, but you don't know, right? So what do? Pick both. At the end, you choose the right answer. It's the fastest adder. So what's the problem with it, though? Yeah.